In the last class, we have read the design of programmable logic array. We have seen that how one PLA can be designed for a set of output functions. Now, today we will continue the discussion on the programmable logic devices. First, we will see that how the what will be the general structure of a PLA design. So, if we consider the one n input m output PLA, then what will be the programmable AND array and the OR array structure. So, first we will consider the programmable AND array. As it is a n input, so there will be 2n number of lines. Say my inputs are I1, I2 to IN and outputs are, these are my inputs and outputs are O1, O2 up to OM. So, this should be I1, I2, IN. So, there will be in the PLA design, there will be n number of product lines. So, number of product lines or the rows are, this is n. So, number of rows in the AND array is number of product lines is 2 to the power n and number of columns is 2n as the n number of input variables and the n number of complemented variables are available. So, this is my AND plane specification, this is my AND. Now, for the OR plane, if there are m number of outputs, so in the OR plane the number of rows are 2 to the power n, the product lines, and number of columns are the number of output functions, that is m. So, these are my OR plane specification. So, now if we draw the PLA, the generic structure of a PLA. So, it has 2n number of input lines. So, if we mark that as a, say, I1 bar, I2 bar, IN up to IN bar. So, these are 2n number of columns. Now, we have 2 to the power n number of product lines. So, these are the 2 to the power n number of product lines. So, here this is actually 2 to the power n, and depending on the program, that means which min terms we have selected, say the cross points will be here, and this is row wise. That means, say for this case it is I1, I2, then say In bar. Similarly, the third one will be say I1 bar, I2, In, like that. So, this is my AND plane. Now, if I draw the OR plane, so 2 to the power n number of product terms, these will be the rows, and there will be m number of columns. So, m outputs, these are my m outputs, and they are O1, O2 up to OM. Now, in the OR plane, the cross points will be column wise, because from the AND plane the min terms are selected, and then this is the sum of min terms. So, say if this is my min terms, and if these are the product lines, say P1, P2, P3 and P2 to the power n, then say O1 is in this structure, say O1 is P1 plus P3. So, here similarly the min terms will be selected. So, this is my programmable AND plane and this is my programmable OR plane. And the size of the PLA is, see that here there are 2 to the power n number of rows, and in the AND plane there are 2n columns, in the OR plane it is m number of columns. So, total columns are m plus 2n, and so the size of the PLA, so the size of PLA having n inputs, and m outputs is equal to the 2 to the power n by, this is the number of rows, by m plus 2n number of columns. So, this is the size, and so these many number of cross points are also available. So, these are my number of cross points, maximum number of cross points. Now, as I already mentioned that if the number of min terms, say if the input variable or the inputs are large, means that is n is large, but only a few min terms are needed to realize the outputs functions. Then the PLA can be minimized and in this case the PLA is efficiently utilized. Now, another case is the for PLA minimization, say PLA can be minimized that number one, that in the OR plane, or first we see the AND plane. In the AND plane, same column is shared by two input variables. Or similarly, in the OR plane, same column is shared by two output variables, output functions, two output functions. In this case, actually the PLA is partitioned row wise, means say if I give a or say I have columns so there are say here I1, say I1, say this can be I2, this can be I1 complement, this can be I2 complement, say this is I3, this is I3 complement. So, here the partitioning has been done like that. This is in the AND plane structure, and similarly if the OR plane, say if there are only two outputs and it is possible that this is O1, so this is O2. So, this can be partitioned like that. So, in this case, as it is a 3 input 2 output function, so the size, actual size needed was size would be the 8 product terms 2 to the power 3, 8 by 6 plus 2. So, this will be, because 2n means 6, 2 output. So, the actual size or original size should be 8 by 8, 8 by 8 structure, whereas here we see that it is only a, the in this case the product terms we are not sharing. So, rows are same. So, the modified size will be only 8 by 4, because here columns are only 4. So, in this case the example I have shown here, actually the columns are sharing by the input variables and the output functions. Similarly, what we can do, the other partitioning for PLA minimization, that can be the if the product terms are shared. So, what we can do, say I have, if for n input variables I have 2 to the power n product terms. Say in my cases here n equal to 3 and m equal to 2, what we have seen. So, 2 to the power 3 there are product terms, p is 2 to the power 3 equal to say 8. Now, if the design is such that it is possible to share the product terms, then instead of 8 what we can do, that say this is as if this is possible. Now, say this is P1, P2, say P4 and P8, and it is P1 is shared by P3, P2 is shared by P5, this is P6 and say this is P7. Now, the columns are as it is, say it is 6 to n, that means there are 6 columns in the n plane, and say in the or plane there are 2 functions, say like this. These are the 2 functions. So, in this case the instead of 8 by 8 we will get the size is say here it is only 4 columns, 4 divided 4 by 8, this is a 4 by 8. Earlier cases it was 8 by 4 if it is row wise shared or row wise partition, that means columns are shared. Here it is column wise partition, that means product terms or the rows are shared. So, in this way the PLA can be minimized. So, now we have seen the programmable logic devices. We are mainly discussing on different type of programmable logic devices structure. So, the PLA structure we have seen and how it can be minimized. Now, there are 2 other different PLDs are available. One is CPLD, the complex programmable logic devices, another is field programmable gate array. Now, we will see in details the design architecture of these 2 type of PLDs. As already we have seen that PLD means that say for this particular design, this is the AND plane, this is the programmable AND plane. So, we have seen this is a programmable on this is a programmable AND plane, and this is a fixed or this is a fixed OR plane, and in these cases the 2 functions f1 and f2 are realized. Now, not only combinational, we have seen that sequential part also can be realized by using this programmable and the fixed type of OR plane. So, any one of these, so far we have discussed the PROM, PLA, PAL can be the PLD block. So, CPLD, the complex programmable logic device, we can define as if this is the integration of several PLD blocks with a programmable interconnect on a single chip. So, these are the PLD blocks, and these PLD blocks can be any PLA, PAL or PROM type of design. Moreover, that IO blocks, that means for the IO interconnections, that can also be programmable, and this some interconnection matrix is there. So, this is the overall architecture of the CPLD. Now, we will read the field programmable gate array, and we see that actually the basic architecture is same, only the technology is different. So, the FPGA building block, that it has some actually it has three type of blocks are available in the FPGA. The programmable logic blocks, which implement combinational and sequential logic. As already we have seen that PLD blocks can realize combinational as well as sequential blocks. Now, programmable interconnect. So, wires to connect inputs and outputs to logic blocks, just now we have seen, see these logic blocks for this wire, this can also be programmable, and for these purposes, just to program the interconnection, actually this interconnection matrix is controlled from outside. So, there are some control lines, or this can also be programmable, or the interconnections are programmable. Now, is programmable IO blocks. So, special logic blocks at the periphery of device for external connections. So, not only the logic blocks and the interconnection blocks are programmable, but the IO blocks, that means the which input we want to feed and which output we want to take from the design, that IO blocks is also programmable. So, these are the three programmable logic blocks or the basic building blocks of FPGA. So, already this overall architecture we have seen. Now, I describe one by one. So, this is again a 2D type of grid structures, and if I consider this as a matrix, so this as if this small green one and the larger yellow blocks, these are the two type of matrix elements, and the yellow one we are telling this is my switch blocks or the programmable interconnection blocks. So, this is my programmable interconnection blocks, and this is my logic blocks. This is logic blocks, and these are the IO blocks, 4 IO blocks as if they are arranged in the boundary. So, these are my programmable IO blocks. So, these are actually connected. This one is connected and these are all bidirectional, and they are connected with the switch box also. So, these connections are also available. Similarly, here also I can connect. So, this type of connections are available. and all the 3 building blocks can be programmable from outside. So, this is the basic architecture. Now, there can be other type of FPGA building blocks, and they are for the clock distribution, the embedded memory blocks, special purpose blocks are DSP blocks, hardware multipliers, adders and registers, embedded microprocessors, microcontrollers and high speed serial transceivers. So, clock distributions, that this is one circuitry and always these are needed. See, if I have if we draw these things, say as if this is my full FPGA and the one switch box, what I can draw, this is one switch box and these are my programmable, say these are my programmable logic blocks, say this type of things. Now, all are connected. See, this type of connections are there. See, I have another switch box here which are connected to logic cells. Now, say this one need a, if it is a sequential circuits. So, this needs a logic cells clock. Similarly, here these cells are also needed clocks. Say here this one is needed a clock or this type of things. So, actually just to avoid the clock skew, because the same clock always we prefer the same clock. So, then the clock should be distributed so that that clock skew can be avoided. So, we need a special circuit for this clock distribution, and nowadays this is so common for the complex circuits. So, this clock distribution circuit itself is implemented and that can be treated as a special type of, this is a special type of building blocks, special type of FPGA building blocks. So, this is my clock distribution circuit. Now, embedded memory blocks. So far we have discussed the logic blocks are combinational and sequential, but all of you know for that complex circuits or any real life circuits we need the memories, lot of memories, and these memories are now they are called the embedded memories within the FPGA. So, for that memory is a special type of building blocks already implemented in the FPGA. Now, so for digital signal processing we need a special type of processing, say some matrix multiplication we needed. So, some matrix multipliers or some fast multipliers, some fast adder or parallel adders, and say set of registers, that all these things are needed. So, these are the normally these are the common processing elements of the DSP blocks. So, they are treated as a FPGA building blocks. Similarly, embedded microprocessor, microcontrollers, that are also treated as a FPGA building blocks. So, nowadays though we call that normally there are only 3 type of building blocks, one is programmable logic blocks, one is programmable interconnection or sometimes we call the switch box, and the programmable IO blocks. But in addition that nowadays the modern FPGA chips, they contain this type of circuitry, and again they are treated as a special type of building blocks. Now, how these FPGA basic logic element are implemented? As in the last class we have seen, I mentioned that normally lookup table is utilized or is the basic concept of a FPGA logic element. So, LUT to implement combinational logic, register for sequential circuits, additional logic, and that is carry logic for arithmetic function or expansion logic for functions requiring more than 4 inputs. These are the some common features of FPGA. Now, this is one very simple or basic logic element. Say I have one lookup table. Say it has 4 inputs, the A, B, C, D. So, there are 4 input variables A, B, C, D are the inputs of the lookup table. Say there is only one output, say one function f, and that can be latched as already we have seen, and it can be selected. So, using this control line as the select, this is my control from outside. When I want to take the output, that can be chosen. Now, lookup table is one of the important, or this is the basic concept. So, lookup table with n inputs can be used to implement any combinatorial function of n inputs, and lookup table is programmed with the truth table. So, we see that how the lookup table is implemented. So, this is one example. As in the example I have shown, there are one lookup table, it has 4 inputs A, B, C, D, and one output Z. So, this is the truth table, and the truth table, this truth table is given the 4 inputs A, B, C, D, and this is one output. Now, see already we are using the Karnaugh map or many other strategies we have read, that we can derive the functions, that what will be the Z, the output functions. Now, what we can tell, or that as if these ABCD are the addresses of the table and Z is the content of the table. So, here this LUT, for this LUT, as if ABCD are the locations or the address of the table, and Z is the content of the table. And if it is Z is some function of ABCD. So, using Karnaugh map, we know that always Z can be realized by using get. This is simple type of get implementation, where say this is AB bar, this is an AND. So, AB bar, and this is a C plus D, CD, or so C plus D. So, this is AB bar to C plus D, this type of Z equal to AB bar dot C plus D. So, this is the function realized. Now, the same thing we can treat as if this is a, that if I give the ABCD values as if that particular content already it is computed and that is kept as a content of the table. So, this mainly this is the basic concept of the FPGA LUT. So, one thing this, so mainly LUT as inputs are treated as address, and these are the address, and output is content. So, this is nothing but a memory. Okay. So, how it is implemented? See, this is one multiplexer based, as if LUT entries stored in configuration memory cells, and so these are the contents of the memory. So, these are the output function, the configuration memory cells means as if output values are stored as the content of the table LUT, content of LUT, and the 3 inputs x1, x2, x3 they will be treated as the address of the memory, and in this way the LUT can be implemented. So, this is one possible LUT implementation, and this is based on multiplexers. Multiplexers are mainly for the programming part, as this is a programmable. So, which one I want to select? So, it is doing that thing. So, now for programmable interconnect. So, LUT is the implementation of programmable logic block. Now, programmable interconnection. So, interconnect means we know that this is nothing but the switching. So, as if I have a fixed wiring, I have a 2D structure of wires, there are some rows and there are columns of wires. Now, which wire to be connected to whom means which row is connected to which column, that is nothing but the switch. So, that is why the programmable interconnection can be treated as a switch box. So, this is one general pictures, say as if say these are some, this is one switch matrix, this is one switch matrix, this is one switch matrix. Now, say I have given, say this is my programming part, it is coming from outside. So, this is LE means latch enable. So, this line is selected and it is, say this is the switch, say it is going to this, say this is another latch enable. So, it will be again depending on this, say as if this output is selected. So, this can be a multiplexer type of thing, again this line is selected. So, this is a switch box and this can be a output. Okay. So, this can be a direct output. Similarly, different type of other connections are available here. This can. So, mainly that some horizontal and vertical lines, what I mentioned, that rows and columns of wires are there, and in between some switching elements are put, and the function of the switching matrix is that which wire to be connected to whom. So, this is nothing but that interconnection, programmable interconnection part. So, in this way the programmable interconnection blocks are implemented in FPGA. Now, if we quickly see that switch matrix operation, because these are nothing but a switch, see that this is before programming, as if the switches are kept, and this is after programming, means which one is connected to which line, as if this is this line is, say this red line means this is one connection, say this blue line this is one connection like that. Now, this is actual switching is, we know that this is by pass transistors, and these are act as a programmable switches. So, pass transistor gates are driven by configuration memory cells. See here that this is a 6 transistor model. We call this is a 6 transistor model. There can be many other models available, and see that from anywhere to anywhere the connections can be, if these pass transistors are selected, then these 2 points are connected. Similarly, if this pass transistor is connected, then this and these points are connected. So, in this way from any point can be connected. Here the model we have taken is that one switch box is here, this is one switch programmable switch box, and as if the logic cells are kept or arranged like that, and these are the connections. So, if I see that, say as if these 4 connections, they are the 4 logic blocks, and to whom which logic blocks to which logic blocks is connected, that is the switch box is doing that interconnection part. So, this is a 6 transistor model, and mainly pass transistors are being used to do that thing. Now, there are some special features, say clock management. Normally the phase lock loop circuit or the direct link clock, and these are being used for clock management, which and these clock managements are needed to eliminate clock skew between external clock input and on chip clocks, and they support various interface standards, high speed serial IOs, embedded processor cores, and the DSP blocks. So, mainly these are the special features of FPGA. Now, the configuration of storage elements. So, as already we have seen that mainly the memory is the basic building block, because LUT is implemented by using memory. So, the storage elements or the content that are kept in the LUT is a static random access memory, SRAM. So, here each switch is a pass transistor controlled by the state of an SRAM bit, and FPGA needs to be configured at power on. Then flash erasable programmable ROM. So, here each switch is a floating gate transistor that can be turned off by injecting charge onto its gate, and FPGA itself holds the program, and this obviously it can be reprogrammable even in circuit. That means, we can get that for one type of control, one type of interconnection, I get one design, and then that can be erased, and next time for the different interconnection I will get a different design. So, it is the reused, it can be highly utilized, especially for the purpose of the academic purposes, or to use FPGA in a laboratory. This type of memories are very much needed. Now, configuration storage elements can be of fusible links. Already we discussed that fuse or anti-fused is used to get the cross points on or off. So, it forms a low resistance path when electrically programmed, one time programmable in special programming machine, and this should be radiation tolerant. Now, we see some example. As I mentioned already, that not only the combinational sequential logics that are implemented by using programmable logic blocks, but there are some special type of FPGA building blocks. One very important thing is the embedded memory, and here we see on this type of structure. See this, in this example, this is a 512-bit RAM block. This is a RAM, and this is a dual port RAM. So, 512 by 1 bit, and these are the different input output lines. As in the memory, we know that normally there should be data in, means this is for my data in is for my addressing part. Or just we see that that which value I want to store, that is my data, and the next line is a clock. Now, this is the data out bit. So, when I want to access the table or the LUT, so this is my data out or the value of the output functions, and this is my address signals or the addresses, means from which locations I want to get the value, and another is the control signals. So, normally this is the structure of a embedded memory, and these are the lines input output and the address lines are available of the chip of a embedded memory. Now, this is another type of architecture we call the logic slice architecture. Again, this is an example, actually real life example. See here, two 4 input LUTs can also be used. This is a complex thing. So, normally so far we have seen only one lookup table. Now, here two 4 input LUT can also be used as 16-bit synchronous RAM, 16-bit shift registers. So, this is my 16-bit RAM, this is my 16-bit RAM. See, two 4 input LUT. So, these are 16-bit RAM, and these are my 16-bit shift registers. This is one shift registers, this is one shift registers, and two flip flops or latches. So, this is one flip flop, one flip flop. So, actually if we see that this is one LUT, as if this is one LUT which contains one 16-bit RAM, one 16-bit shift register and one flip flop, and this is another LUT. This is another LUT which has the same contents, and there are 4 inputs. There are 4 inputs. So, actually this when that this is a lookup table, how it is implemented? That means, this lookup table is of 4 input bits, and then first width expansion logic. So, implement logic functions with more than 4 inputs. Okay. So, now these are my arithmetic logics which is also available, and this is some register latches. See here, actually the connections are not shown, these can be programmed according to the design. So, this is a normally called LSA or the logic slice architecture. So, in this particular example, actually 2 4 input LUTs are used, but for other complex circuits more than 2 or actually n number of LUTs can be there. In real life circuit, actually the switch box, the picture we have seen, the 2-dimensional matrix or 2D grid structure, where one interconnection matrix or one interconnection programmable interconnection block is connected to. So, if we see that thing, see here that one interconnection block is actually connected with the logic blocks, these logic blocks, and this. So, number of LUTs can be there in a FPGA, and this is actually how just now what we have seen, that how actually they are kept or they are implemented. So, this is a logic slide architecture. Now, we have seen some embedded memories. Nowadays, for say DSP type of circuits, multiplier is a common processing element. So, the multiplier itself can be pre-designed and can be kept as a basic building block in the FPGA. So, this is one Xilinx example of embedded multipliers. See here, so that switch matrix is connected to 18 kbit block select RAM. So, this is my RAM and this is a 18 by 18 multiplier, as if this is the Xilinx, the pre-designed multipliers that it kept as a embedded multiplier in the FPGA. One thing to be noted, that this can be a different type of architecture, because when we will read later the different type of design of multipliers, we will be seeing that this architecture can be changed. This is one example. Now, these are different embedded DSP blocks that Altera family has, that they can be kept as a FPGA building blocks. So, here 2 DSP block columns per device, number varies by height of column, and they can implement. So, actually what are the processing they are doing, or the what are the functions, that 8 9 by 9 multipliers. So, they can implement multipliers, 4 18 by 18 multipliers, 1 36 by 36 multipliers. So, these are 3 different type of multipliers, and see the numbers are also different, and that can be implemented. They contains adder, subtractor or accumulator, and then registered inputs can become shift registers. So, this can be normally for digital signal processing, we need the multiplication, addition, subtraction, and for that purposes as if the building blocks are kept. And see here, these are actually configurable, reconfigurable. So, the different type of multipliers can also be implemented. Now, this is another example of which has been taken from Altera family, that embedded DSP blocks. Now, if we see that what are the different building blocks kept here. So, see there are 4 18 by 18 multipliers, just now we have seen. See, these are adder, subtractor, accumulator, adder, subtractor, accumulator, and these are some summation circuits. So, this is overall embedded DSP blocks. Again, this can be treated as a basic building block for DSP type of FPGA. So, not only that multipliers or the adders are the building blocks, this is a together, this can be again. So, actually the design is a hierarchical. So, we have seen the different type of programmable logic devices. Today we have discussed the FPGA, which is the state of the art technique for VLSI design, and earlier we have read the basic things PLA, PLA, etc. So, these are the lecture 27 and 28 quizzes. So, mainly the what is programmable logic array, whether how does it differ from PAL, and then what is FPGA and the different building blocks of FPGA, and another thing is that how the programmable logic blocks or the LUT lookup table in FPGA is implemented, and what is LUT. So, these are the quiz questions from the last two lectures, and we end the discussion of programmable logic devices here. So, today's lecture is on design of arithmetic circuits. In this class, we will read that how we can design the different type of adders, multipliers and other arithmetic units. As the adder is the most important and the mostly used digital circuits in a digital system. So, first we will see that the different type of adder design and its performances, and which one is suited for what type of design, etc. So, first we start discussion on the adder design. As all of you know that what is the truth table of 1 bit adder. So, if we know that if it is a 1 bit, mean the bit can be either 0 or 1. So, there are different 4 possibilities, that either 0 is can be added with 0, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1. In all these 3 cases, the carry is 0, carry is 0. Now, 1 plus 1 is 1 0. So, if we see that binary, this is 1 1 1 and actually 1 0.